Okay, for our third segment, we will now start with the solutions to the further question about dogs 1 and 2. We went back to the problem of the 3 dogs pulling on a stick, and we found the work done by dog number 3, work being the dot product of the force vector times the displacement vector. And the displacement vector was given in the original problem as d equals negative 7.9 times unit vector j minus 4.2 times unit vector k. And the force equations for each of the dogs was given in the original problem. There it is again here. And so we're going to need that similar information to solve for the work done by dog 1. Vector d, that is the displacement of the stick, is the same for dog 1 as it is for all the other dogs. And we also need the equation for the force exerted by dog 1, which, if we go back to the original equation, is F1 equals 10I minus 20.4J plus 2K newtons. So the work done by dog 1 is just the dot product of vector F1 with vector D, and that means the x components multiplied together plus the y components multiplied together plus the z components multiplied together. In practice, that's going to be 10 newtons times 0, because notice again in the displacement equation there is no term for I, unit vector I. So that means that the magnitude of unit vector I must be 0, or the magnitude that's being multiplied by unit vector I is 0. So 10 newtons times 0 centimeters means 0. So that term drops out. The second term, the y components, negative 20.4 newtons times negative 7.9 centimeters, plus the z components, we've got 2 newtons times negative 4.2 centimeters. And so when we multiply all this out, we get 161.16 newton centimeters minus 8.4 newton centimeters. So that's 152.76 newton centimeters for our work done by dog number 1. Of course, that actually is a valid unit for work, because it gives a force times a displacement. But again, the customary units for work would be Newton meters or joules. And although, if on a test or a quiz or something, if I didn't specify what units I wanted you to use for the answer, then you could leave the answer in this form. But most likely I would specify joules or Newton meters, which would mean that you have to change Newton centimeters to Newton meters. So again, you just take the number of Newton centimeters, divide by 100. That way the centimeters cancel, and you get 1.5276 Newton meters or 1.5276 joules. Okay, so that's the work in joules. If you haven't already figured out the work done by dog 2, then take this opportunity to pause the video and try to work it out yourself and see what you get. And then we'll compare results once you're done. So pause the video. And okay, if you're coming back now, or if you've already done it, then hopefully you'll get something like this. The vector for the displacement remains the same as it was for the other 2 dogs, because it's the same stick and it's moving in the same amount in the same direction. The force vector for dog 2, we have to go back to the original problem for that, and that is negative 15I minus 6.2K newtons. So the work by dog 2 is just the dot product of vector F2 with the vector D. So again, it's the x components multiplied by each other, plus the y components multiplied by each other, plus the z components multiplied by each other. That's negative 15.0 from here. That's in newtons times, 0, because notice there's no I term for the displacement vector. So the x term or the x component would be 0. So that means that whole term drops out. Plus the y components. Let's see, for F2, notice there's no j. So the y component of F2 must be 0. So that's 0 newtons times negative 7.9 centimeters. But that's 0 also overall. So that drops out. And that leaves us with the z term controlling everything, or the z direction controlling everything. And that is going to be negative 6.2 newtons times negative 4.2 centimeters. And that ends up being 26.04 Newton centimeters. But again, if you want it in joules, you divide by 100 so that centimeters become meters, and you get 0.2604 Newton meters, which is the same as 0.2604 joules. So that's the work for dog 2. The question never asked, but it might be interesting to figure out how much work was done by all 3 dogs combined. Well, the total work, which is what T stands for here, total, is just going to be the work done by dog 1 plus the work done by dog 2 plus the work done by dog 3. So just add them all up, and that's 1.5276 plus 0.2604 plus negative 0.9875. And so this is dog 1, dog 2, and dog 3. Remember, we did dog 3 first. That's why these are out of order compared to the order we did them in. And anyway, you end up with 0.8005 joules. That's how much work was done in total. You have 2 of the dogs essentially working in the same direction and 1 dog working in the opposite direction. So that's why this one ends up being negative, and you end up with 0.8005. All right, so that is an overview of dot products for vectors. Hopefully that's making sense. There's some homework problems that will help with that also, I hope. So now we need to come to the other type of multiplication of vectors, which is known as the vector product or the cross product of vectors. I, again, tend to refer to this as the cross product because calling it cross product conveys directly how it's represented. So the cross product is represented as vector A times literally X vector B. All right, so vector A X vector B, that is the cross product, is a vector that's perpendicular to both A and B. In other words, well, any 2 vectors can be considered as being in a plane. Because you can always draw a plane that will include any 2 vectors. The cross product of those 2 vectors will be perpendicular to that plane that contains those 2 vectors. Okay, this is a diagram on page 83, which shows the situation better than I can draw it. So I'll just show you here. The cross product of vectors A and B would be this vector here. You can see that you can draw a plane that has, or you can arrange a plane anyway, that contains vectors A and B. If you take the cross product, then that vector is perpendicular to both A and B. The angle between 2 vectors for a cross product is measured in a certain direction. The direction of the angle, or the direction in which the angle is measured, does matter for a cross product. You go from the first vector listed to the second one. So if you're taking the cross product of A crossed with B, then you have to measure the angle from A to B. And if you're taking the cross product as B crossed with A, that is the opposite direction, then the angle has to be measured in the opposite direction from B to A, because B is first now. And you'll notice that the result goes in the opposite direction. So it turns out that cross products cannot be done in any order. If you change the order of the vectors in a cross product, you're essentially getting the negative of the vector that you would get for the other order. So A cross B is vector C, B cross A is vector negative C. Same magnitude in exactly the opposite direction. Still perpendicular to A and B, but pointing exactly opposite to the direction that it otherwise would if you went A times B. Okay. All right, the magnitude of a cross product is AB sine of phi. And again, phi is the angle measured from the first term in the cross product to the second term in the cross product. So here it would be from A to B. But if you switch this around, the angle would have to be measured from B to A. And the angle is always between 0 and 180. And the vector product ends up being 0 if A and B are parallel to each other, because if A and B are parallel to each other, phi, the angle between them, would be 0, and the sine of 0 is 0. And the vector product is also 0 if vectors A and B are anti-parallel to each other. Because if they're anti-parallel, then the angle between them is 180, and the sine of 180 is also 0. So that's what I'm saying here. Sine of 0 degrees is 0. Sine of 180 degrees is also 0. As I mentioned a moment ago, reversing the vectors in a cross product produces a vector that's anti-parallel to the original product vector. So again, like the example that I just showed from the book, if A cross B equals C, which points up, then B cross A would be negative C, which points down. Or you can look at it as A crossed with B is equal to the negative of B crossed with A. In other words, this is what's known as being anti-commutative. You can't just do it in any order you want. You have to do it in the order that's written. If you reverse the order, you get the negative of what you would have gotten originally. All right, in order to determine the direction of the vector product, you can use what's known as the corkscrew or right-hand rule. And this is on page 84, where they show an illustration of that. Okay, there is the corkscrew rule. And what they're showing you is you think of the result of the cross product as being like a corkscrew, and you're turning the handle of the corkscrew in the direction from the first vector to the second vector. And if you do that, it'll tell you which way the resulting vector of the cross product should be pointing. So in other words, the corkscrew is placed perpendicular to the plane containing A and B, and the handle is turned in the direction from the first to the second vector in the product. If it's A cross B, then you turn the handle from A to B. Okay, so you can basically think of yourself as having a corkscrew that is in this position here, pointing basically straight up at you. and you are turning it so that the handle goes from A to B. In other words, you're turning it clockwise. Okay, one of the advantages to doing these lectures from home via video is I don't have to pretend that I have a corkscrew, because I do have a corkscrew. So essentially what you're doing is you're putting the corkscrew right there at the origin of vectors A and B, and you're turning the handle in the direction from A to B. In other words, clockwise as you look down at it, like this. And what happens with a corkscrew when you turn the handle clockwise is that it goes down into the paper. And so C, the resultant here, or the result of this cross product, would be below the paper, like that. Okay, if this is A crossed with B. If you have the same vectors within the limits of my artistic ability anyway, and you're considering this to be B crossed with A, then you'd take your corkscrew and you'd put it at the confluence of the two vectors, and you would turn the handle from B towards A, in other words, counterclockwise. Okay, and what happens when you turn a corkscrew in this direction is it comes out. Okay, so in other words here, vector C would be above the paper and go up. So we're essentially, the corkscrew rule is the old rule of righty-tighty, lefty-loosey. It basically, it's like any kind of screw will obey these rules, except for those few screws here and there that are threaded backwards for some reason. But normally, if you're turning counterclockwise, or if you're turning clockwise, you're going down. And if you're turning counterclockwise, you're coming up. Okay, so that is how you can find the directions. Basically, clockwise is down, counterclockwise is up. An example of using this kind of information is in calculation of torque. Like I said, torque is a turning or twisting force. It's the kind of thing that you're dealing with if you're, say, screwing in screws or taking screws out, or nuts or bolts or things like that, because you're trying to force something to turn around an axis. And the general equation for torque is force times lever arm. I mentioned this before. Lever arm, well, force is a vector, of course, and lever arm is, for instance, the length of a handle of a wrench, or rather the length of the distance from the center of the bolt to where your hand is on the wrench. And it has a direction going from the bolt to your hand. And so lever arm is also considered to be a vector. And torque is force crossed with lever arm. And so it is a cross product of vectors. Basically, what we're saying is that if a certain force is, or if a certain torque is required to loosen, say, a lug nut on your wheel of your car, then you need a certain force exerted at a certain distance from the lug nut in order to get it to come off. If you increase the distance away from the lug nut where you're exerting the force, in other words, if you increase the lever arm, then you can reduce the force. So in other words, if you've got a lug wrench on the wheel, on the lug nut on the wheel, and you're holding the lug wrench right up near the bolt, and you're trying to get the bolt to come loose that way, you're going to have to exert a lot of force. because the lever arm is very small. If, however, you grip the lug wrench way out at the end of the handle, then your lever arm is greater and you can use a smaller amount of force in order to get that lug nut out or off. Mechanics actually have things that they call cheater bars. It's basically like a length of pipe that you can slip over the lug wrench or any other wrench for that matter, which effectively increases the length of the handle of the wrench even more. And some of these cheater bars are really long, like 4 or 5 feet long. And you can go out to the end of that and you can actually get the lug wrench or the lug nut to come off with very little force at all, because you've got a huge lever arm. And so that's essentially what we're talking about here. The mechanical advantage of a wrench is basically just how much work you save or how much less force you have to use to do a job based on basically the length of the wrench and where you hold it. So the mechanical wrench of a length depends on things like the magnitude of the force that's applied, on the direction of the force, hopefully you're pushing it in the right direction, and how far from the nut the force is applied, or in other words, the lever arm. In the examples in the textbook, they're using R, presumably for radius, to represent lever arm. The quantity that's called lever arm in a lot of physics books anyway. And the distance R from the nut to the point where the force is applied to the wrench handle is given by the radial, there's your R, vector R. So in other words, that's the lever arm. The application of force F to the wrench at a distance or lever arm of R results in a torque, which again is lowercase letter tau from the Greek alphabet, which is a vector itself, which actually is what actually turns the bolt. So in other words, torque, that is vector tau, equals vector R crossed with vector F. And here's an actual example where we, in order to loosen a rusty bolt, 20 newtons of force is applied to the handle of a wrench at an angle of 40 degrees to the wrench handle axis and a distance of 0.25 meters from the center of the bolt. And that's figure 2.31a on page, I think it's 85. Okay, so here's your situation. Here is R going from the center of the bolt. They call it a nut in the text, but if you actually look at it, it's not a nut, it's a bolt. Going from the center of the bolt to the point where the force is exerted on the wrench handle, and the force is being exerted in this direction, which is an angle of 40 degrees to the axis of the wrench handle. And of course, if you really want the force to be maximized, you're going to be pushing straight up rather than off to the side like that. But that remains to be demonstrated. So we'll leave it at that for now. Okay, so what they want you to do is find the magnitude and direction of the torque on the bolt. And B, what would be the magnitude and direction of the torque if the angle were 45 degrees instead of 40? And for what value of phi, that is at what angle, does the torque have the maximum magnitude? All right, so if we consider that vector R and vector F to be in the XY plane, with their origins at the center of the bolt head, vector R points along the wrench handle, as we saw in the diagram that I just showed. R is the reference point for measuring theta because it's the first in the vector product. And so we know that tau equals R crossed with F. Tau must be along the z-axis. In other words, perpendicular to R and F. So for part A, the corkscrew rule for R crossed with F gives plus Z as a direction. In other words, if you translate R and F so that they have the same origin, this is something the book didn't mention. So this is an important point, because if you try going in the direction from vector R to F, as they're shown here on the diagram, you're going to get the corkscrew going clockwise. And you're going to think that you're going to be screwing the bolt in. But obviously, if you're applying force this way on the wrench, this way on the wrench, you're going to be unscrewing it. So how do you get that you're screwing it in if you're obviously unscrewing it? The catch is that in order to judge the direction, you have to translate vector R so that it has the same origin as vector F. So we've got vector F and vector R pointing this way. Now, if you go from R to F, you're going that way. So there's the trick. You're going counterclockwise in the corkscrew rule, which means you're unscrewing the bolt, and that the result is going to be coming out of the paper towards you. In other words, you're unscrewing the bolt. Okay, so I've done that here, and you notice that you're going counterclockwise. So in other words, the bolt is being unscrewed. Force is 20 newtons and R is 0.25 meters. These are the magnitudes. Tau is going to be, that is the magnitude of the torque, is going to be the absolute value of the vector R crossed with the vector F. That's RF sine theta. So that's 0.25 meters times 20 newtons times sine of 40 degrees, or 3.21 joules. Oh, sorry, 3.21 joules. Okay, for part B, the corkscrew rule says that basically you're going in the opposite direction now, because notice in B, they're actually measuring the 45 degrees from the other side of R. So this is 45 degrees here. If you translate R and F to have the same origin, and you go from R to F, now you're going clockwise, and you're screwing the bolt in. Okay, so the direction says we're going in the negative Z direction. In other words, we're going down into the page or screwing the bolt in. The magnitude of tau should be the absolute value of vector R crossed with vector F, and that's RF sine theta. So that's 0.25 times 20 times sine of 45, or 3.53 joules.
Can you pause it?
Just a second. And when they're asking for the largest value of the torque for this or any given situation, it's at an angle with a maximum value of sine, because R and F for any given situation are going to be the same no matter what angle of you're applying the force at. What's going to change would be the value of sine of phi. If you're changing the phi, then you're changing the value of sine. Well, the maximum value of the sine function is 1, and that occurs at an angle of 90 degrees. In other words, perpendicular to the handle. So that's what I was getting at when I was saying it's kind of stupid to apply the force at a weird angle like that. You'd want to push directly up on the handle, because that's where you get the maximum force. And indeed, 90 degrees to the axis of the handle is where you get the maximum force, because that's the maximum value for sine, for the sine function. So the maximum value for torque would be RF sine of 90. In this case, that would be just RF, which is, because sine of 90 is 1. That would be 0.25 meters times 20 newtons. That's 5 Newton meters or 5 joules. Okay, we've gone a little over time for this segment, so I'm going to end it there and we'll pick up in class next week. See you then.